For coming here. This was part of my work back in AT&T, where I was there like until last September. And this was actually my very first InfoSec project. Oh, sure. This is actually my very first InfoSec project in machine learning, data science, whatever you call it. And after that, it's been like a eye-opening experience in the past 1 year in AT&T and my current company in Splunk, that there's so much domain knowledge out there and so much interesting statistical problems out there. So this is, I'm really amazed by the quality of technicalities in my previous talks. So nothing compared to that, but mostly a pedagogical journey of a statistician and a data scientist trying to learn the ropes in this domain. And while doing that, trying to bring in some new ideas. So of course, we all know botnets are bad. And it's useful to monitor botnets. But that's easier said than done. And while doing that, it's not only important to detect botnets, but there are also some related stuff that you can do. For example, sift through alerts that are very frequent, figure out true positives, prioritize alerts, things like that. And coming to the technical challenges, of course, that has been touched upon in the previous talks, is that part A, extreme rarity of signals. Botnets are pretty rare. Secondly, data and label quality. Thirdly, there is a balance that we need to maintain between the cost of false negatives and the cost of verifying positives, in the sense that negatives can bring down whole systems, whole networks, whereas verifying positives is often difficult and might require things like deep packet inspection, which are costly. And sort of a related topic, which this talk is going to focus on, is proper featureization, in the sense that, and in the context that we are going to deal with, that is botnet detection from NetFlow data. And NetFlow data is, of course, something that is very well known in the industry, which is essentially very large scale data about network traffic, IP traffic, and consists of very small amount of features, but the data is voluminous. And the signatures you're looking for in that data, like botnet or different types of other threats, are very, very rare. So it's really, really the case of finding needle in a haystack. And the motivation we are approaching this talk from is that the signatures that we're looking for, the signatures of botnets we're looking for, really exist in the tails of the distribution of the features that we're looking at. For example, packet size. For example, number of packets transferred. The type of botnets we're trying to detect here, specifically command and control servers, if you look into their signatures, you see that most of them have very specific types of feature distributions. For example, the bytes transferred or the number of packets transferred compared to benign or unknown IPs, a C2 server signature is going to look a lot different. And keeping that in mind, if you use some kind of static summaries of these features, for example, means or standard deviations, you would often miss out on those signatures. And that's what we're trying to show here, in the sense that in the left plot, we see that compared to unknown IPs versus C2 IPs, if you look at average packets to bytes ratio, there is a lot of overlap, and basically the same thing for the standard deviations. But for the same feature on the right side, and that's our current analysis is based on, if you look at the same thing, you'll see there is a lot of difference between the two classes, specifically on the two tails. And this difference is not that noticeable in this plot, but if you do a log of the y-axis, this difference becomes even more prevalent. So that's the basic idea that this talk is based on, in the sense that we looked at a bunch of features, saw that the distributions of the positive label versus the unknown label are very much skewed for the positive label, and based on that, we featureized based on the quantiles of those features, and compared that to the static summaries of the features. While doing that, we also did something that we found was not done in many papers that we studied, was a C2-centric analysis, or a host-centric analysis rather, in the sense that we looked for the source IP. We looked for predicting the labels of the source IPs as compared to predicting the labels of the destination IPs. And the reason we thought this would be important, specifically for our purpose, for the featureization that we are looking at, is that for a source IP to be classified as C2 server or not, you are more likely to find a lot of differentiating signatures. Like a C2 server will contact a lot of other IPs, and it will transfer a lot of packets, a lot of bytes, as compared to a device IP. If you do a device-centric analysis on the left side, the signatures will be much more sparse, based on much less amount of communication with hosts. Some of them, or very, very few of them, are likely to be a C2 server. So that's the basic idea. It's classifying. The classifier model we'll finally be looking at is to classify whether an IP is C2 or not. And that is being done based on featureizations of these fundamental features that are part of standard NetFlow datasets. For example, source IPs, destination IPs, source ports, destination ports, bytes transferred, packets transferred, and everything else. So the basics here, I wouldn't go through. This is kind of a pedagogical slide. But the way this plugs into the overall system that we analyzed is to kind of prioritize the positives, specifically in the sense that there is a thread platform through which the labels are flowing in, and based on after that we are applying the machine learning model, outcomes of which are getting filtered through a deny list, and they are getting passed through a DPI system to feed into enriching the deny lists and being updated time over time. So that's the basic idea, pretty simple. And delving a little bit deeper into whatever I was talking about before is the fact that the distribution of the features that we are looking at is really skewed for a C2 server, which you can see in the left plot, in the sense that the quantile plots for the specific feature that we're looking at, I think it's packet size. So that specific feature that we're looking at is really skewed for C2 to bot connections as compared to normal connections. And that gives us some kind of a rationale of looking into these tails into more detail. Another rationale of doing a C2-centric analysis is the right side plot, which is kind of a time series plot of how many connections happened from C2 to bot versus normal, in the sense connections between normal IPs. And you can really see that because we are taking a C2-centric analysis, because we are taking a C2-centric approach, we can really look for these rich connections. So if we can featureize well, we can find out these rich, dense connections, which are really sparse in the sample space, well, as compared to normal connection between a normal source IP versus normal destination IP. So the data we specifically looked at was daily flow data processed through a telecom service provider, and the specific data set that we used belonged was an aggregation. The labeling was an aggregation between several malicious botnet families. And of course, that data was pretty sparse. So we did some kind of data enrichment, basically, which involved sampling a number of IP addresses, 1,000 IP addresses for every day from the majority class, and then using all the positive samples from the malicious class. This gave a data set that was a little better. That was quite a bit better, actually, from the actual data set in terms of the proportion of the positive samples. And we did that for the month of December 2021 and tested that for the next month. That was our test data set. So trend test on December, of course, keeping the forecasting part intact, and then actually do out of sample validation on the next month's worth of data. Finally, coming to the nitty-gritties of the model itself, the features that we used were flow size features, for example, bytes transferred, packets transferred, your usual suspects, average bytes to packets ratio, and of course, wherever you have more than one feature, more than one value for a certain sample, for a certain IP address, we use static summaries like means or standard deviations. There are also beaconing features to look specifically for beaconing behaviors that look more into the, time series aspects of the data sets. For example, interarrival times, for example, standard deviation between the interarrival times, for example, the time gaps, summaries of those features. And finally, the novel distributional features, which are basically quantiles of the features at IP level. So what do we mean exactly when we say quantile, and what exact difference does it have with kind of a static summarization of the features is summarized in this slide. And just to simplify the problem a little bit, if you think about just using 3 input features, packets, bytes, and packets to bytes ratios, and suppose the indicator variable is a function of these 3 features, right? But if you really think about it, the NetFlow data is IP to IP connection level, right? So your input features, if you're trying to model an IP, your input features are actually probability distributions. They're not samples. And so in that situation, what we generally do is, if they're distributions, they must be symmetric, right? So that's why let's just use means and standard deviations. That's not always the case, of course. That is wonky, specifically in the situations when we are looking for something very rare. We are looking for IPs that are very rare and belong to malicious families like botnets, C2 servers, or other types of threats. So in those situations, means or standard deviations have 2 problems. Firstly, that the distributions, IP level distributions, tend to be very skewed. And secondly, often the IP level distributions don't have that many samples. And in those situations, standard deviation specifically does not make much sense. So in that case, what we thought would be interesting is to just take some kind of summary of the probability distributions that are more informative, basically, than the means or standard deviations. And what we thought we could do is that just take a bunch of predefined quantiles. Here we take n equal to 20, take n predefined quantiles, and just use those quantiles of that specific distribution. For example, if you have 50 samples, just take quantiles of the distribution, 5 percentile, 10 percentile, up to 95th percentile. Those will be your input features, summarizing that specific input feature, summarizing that specific input feature distribution. And so what happens is that for a certain IP level, you will have a 20 length vector summarizing the packet size, 20 length vector summarizing the byte size, 20 length vector summarizing the packets to bytes ratio. So in a nutshell, that is what we're doing here. And just to be cautious, we are going to append these types of distribution summaries with the static summaries and try to see that whether that produces a delta in prediction. The good thing is that the encouraging thing is that they do. Otherwise, I wouldn't have been giving this talk. And the second encouraging thing was that computing these summaries are not really that hard, actually. To produce quantiles, what you're doing is basically just sorting. So it's just n log n complexity to get these extra features. And as we can see, that does give better predictions across most of the algorithms that we tried across different types of like modeling paradigms like lasso and random forest. So, and also we did the same thing for ensembling approaches as well, just model averaging across different models. That also gave a better approach. In addition to that, something I'll mention that this result specifically was done based on appending distribution summary features of only those 3 features that I mentioned before to the features that I already mentioned even before. So to these 2 sets of features, we added distribution summaries of packet size, byte size, packets to bytes ratio. And so that seems to do pretty well to warrant further considerations. And finally, a little bit of interpretability as well, in the sense that if we look at the variable importances, we can see that really the tail quantiles are what are making the differences, in the sense that most of the quantiles that come up as very high importance are actually all of the top features are quantile features, even in the all features model. And on top of that, 14 of the 20 features, 20 quantiles are like tail quantiles on the left or tail quantiles on the right. So that was also a second layer of validation, apart from the EDA plot that I had shown in the beginning of the talk. So long story short, this seems pretty encouraging, especially in the advent of new types of research that is coming up in the world of distributional data, specifically based on things like Wasserstein metric and variations of Wasserstein metric, like sliced Wasserstein and things like that, to work on manifold value data sets. So given the complexity of data sets that we have in this domain, I think there is a lot of opportunity to apply these types of more conscious featureization approaches, as I would say, as compared to just throw it in a BART model or just throw it in a deep neural network model to get implicit features. There is a lot of opportunity to do this kind of explicit and interpretable featureizations, which a few of my previous few of the talks that came that were before me, they touched on as well. Another good thing that you can do is apply deep learning models on these features, because the featureizations that we're doing, they're pretty big. Like from one input feature, we can produce as many distribution features as we can. So based on that, that actually gives like presents the scope of building highly overparameterized models, which you can do using deep learning methods. Secondly, again, more involved modeling approaches could involve more sophisticated ensembling methods, for example, model averaging. And finally, things like separate models for separate malware families, modeling this as a multi-class classification problem as compared to single class, while tackling these data challenges, for example, labeling difficulty and data quality challenges. So I'll end there. Thank you so much, and I'm happy to take any questions.